The universe is ablaze with light, 400 billion stars in our galaxy alone, each one a potential home. There are more planets than grains of sand on Earth. More time has passed than we can fathom. And yet, nothing. No signals, no structures, no voices in the dark, just silence. A silence so complete, it feels less like absence and more like a choice. Why? Where is everyone? The numbers say we should not be alone, but we are. And if we are, the question isn't just where they are. The real question is what happened to them, and are we next? Please like and subscribe, because this journey will change how you see our place in the universe. Prepare yourselves. We begin. The Fermi Paradox is the most famous expression of this tension between expectation and reality. Named after physicist Enrico Fermi, who never actually set out to find aliens, it was born from a simple lunchtime thought. "Where is everybody?" he asked, while colleagues joked about flying saucers. The question wasn't meant to be profound, but it cracked open the quiet. In a galaxy filled with billions of stars older than our sun, where even primitive radio signals could, in theory, span interstellar distances, Fermi's question still hangs like an echo we can't explain. What haunts us isn't the lack of evidence, it's the weight of probability. It's what came next. In 1961, the Drake equation tried to give us answers. 7 variables, 1 outcome. How many civilizations exist in the Milky Way right now that we could detect? The result, depending on your optimism, was thousands, maybe millions. At the time, we hadn't even confirmed a single exoplanet, but the idea stuck. It whispered of crowded skies and galactic neighbors just waiting to be heard. Then came Kepler. In 2020, after years of silent work, the Kepler Space Telescope revealed what many feared to be true. The odds were even greater than we thought. Over 300 million potentially habitable Earth-like planets, rocky worlds, orbiting sun-like stars, sitting in the habitable zone where liquid water could flow. This wasn't science fiction anymore. It was a census of possibility, a sky overflowing with chances. And yet, again silence. But now the paradox deepens, because not only do we know the universe should be alive, we know that most of it orbits red dwarfs. These aren't just stars. They're the backbone of the galaxy. 8 out of every 10 stars in the Milky Way are red dwarfs, small, cool, long-burning stars that will outlive our sun by trillions of years. Statistically, this should mean something. These stars burn stable, their planets are close, there's light, there's heat, there's time. So where is life? This is the red sky paradox, a cosmic contradiction that hits harder the longer we stare. If red dwarfs dominate the sky, and many have Earth-sized planets bathing in their warmth, why hasn't life lit up the galaxy in red? One answer is that red dwarfs are violent in their youth. They erupt with solar flares that could strip atmospheres bare, radiation storms that could boil oceans and blind evolution before it takes its first breath. But those storms calm. Eventually, these stars become the most stable sources of energy in the cosmos. Planets that survive could bask in near-eternal twilight. Still, we see no cities, no satellites, no technosignatures. Maybe life under a red sun is doomed from the start. Tidal locking is another threat where one side of a planet always faces the star in eternal day, while the other freezes in endless night. But even then, there's a possibility of a habitable band in between the twilight zone, a narrow ribbon where temperatures could be just right. And if evolution favors resilience, wouldn't life adapt? Wouldn't it find a way? What if it did, but it never made it past microbes? Or what if it did, and it's hiding? This is the sinister edge of silence. It begins to look like a decision, a strategy, a survival instinct. Some scientists and philosophers now entertain a darker possibility, that civilizations either hide or die. And here's the deeper fear. If most stars are red dwarfs, and if those systems offer the longest windows for life to evolve, and yet intelligent life only appeared around our yellow dwarf, What does that make us? Special or a mistake? The Copernican principle tells us we are not the center of anything, not time, not space, not significance, and yet Earth feels like an exception. The data doesn't lie, life emerged here. Intelligent life, and nowhere else, as far as we can see. That either means we're first or we're alone. But maybe that silence isn't from absence. Maybe it's from aftermath. Because what if we're not the only ones to have asked the question? What if others asked it first and never lived to hear the answer? The Fermi Paradox once whispered, "Where is everyone?" Now it feels more like, who was here before us? And what did they leave behind? Look long enough into the silence, and it starts to look back. Time is supposed to move forward. That's what we're told. One second after another, ticking in perfect order, like footsteps on a staircase. Cause, then effect. Action, then consequence. But what if time isn't a line? What if it's a mirror folding in on itself, creating loops, echoes, and impossibilities? Because some questions don't just keep scientists up at night, they tear at the very fabric of reality. Imagine holding a book in your hands, Hamlet, by Shakespeare. You know how the story ends. But now imagine you travel back in time and hand that book to Shakespeare himself before he ever wrote a single word. He reads it, copies it, publishes it. Centuries pass, and that very copy ends up in the same bookstore where you first found it. So now, who wrote Hamlet? This is the Bootstrap paradox, a riddle of causality where an object or an idea has no true point of origin. It simply exists, past in a loop between past and future. It's the kind of mind-bending paradox that science fiction adores and theoretical physics can't fully resolve. Because once you tamper with time, you don't just bend it, you risk breaking causality itself. Take another paradox, a darker one, the grandfather paradox. You go back in time, you remove your grandfather before he has children. The future changes. Your father is never born, and neither are you. But if you were never born, then who went back in time in the first place? This isn't just storytelling. This is the edge of physics, because the math allows for it. Einstein's equations, so elegant and powerful, don't prohibit time loops. In fact, solutions like closed time-like curves are baked into the fabric of general relativity. Under the right conditions, rotating black holes, traversable wormholes, or exotic matter, space, and time can twist into loops. And yet, something about it feels wrong, unnatural, like the universe is trying to protect itself from us, as if reality carries a failsafe, a way to snap back if you push it too far. Some physicists believe paradoxes can't actually happen, that the universe finds a way to self-correct, like a timeline immune system. If you try to kill your grandfather, something will always intervene. You trip, the gun jams. History rewrites itself to preserve causality. This is called the Novikov self-consistency principle, and it suggests we can't break time, we can only fulfill it. But others believe the moment you interfere, you fracture reality. One timeline becomes two. You don't erase yourself. You just slide into another version of the universe where you never existed. The old you still exists, in the world you left behind. But you're now part of something else. This idea forms the foundation of the many worlds interpretation, a theory where every decision, every possibility, splits the universe into countless branches, infinite timelines, infinite versions of you, some successful, some ruined, some who never asked these questions, and some who went too far. Time travel, then, becomes less about visiting the past and more about creating new presents. But what if you didn't need a time machine? Enter the wormhole, theoretical tunnels through space-time, linking distant points not just across space but across time itself, a shortcut through the universe's geometry. In theory, if one end of a wormhole experiences time dilation, say, by orbiting a black hole or traveling at relativistic speeds, then time inside it flows differently. Walk through one end and emerge in the past. Now imagine a billiard ball rolling toward a wormhole entrance. If it enters, it loops back in time and exits before it went in. But here's the twist: it strikes its earlier self, just enough to deflect it, preventing the ball from entering the wormhole in the first place. A paradox, a causal contradiction. But the math doesn't explode. In fact, physicists found solutions. The ball can hit its past self, just slightly altering its trajectory in a way that allows both events to occur without contradiction. Not a collision, but a glancing blow, a cosmic whisper, reality finding balance again. Time, it seems, is flexible, but not lawless. Still, we're not done, because one star in the sky broke everything. Its name is HD 140283, but most know it by its nickname, the Methuselah star. Located in the constellation Libra, it moves fast 1.3 million kilometers per hour, and it's old. Older than it should be. Early observations suggested it was 16 billion years old, a problem, since the universe itself is only 13.8 billion years old. How can a star be older than time? Astronomers panicked. They recalculated, factored in uncertainties in distance and luminosity. The new estimate? About 14.5 billion years, with a margin of error wide enough to let it barely squeeze under the age of the universe. But the damage was done. A star older than the cosmos? That's not just a measurement error, that's a wound in the narrative of space-time. A reminder that even our most precise instruments may be looking through a warped mirror, that what we see out there might be reflections of things we don't yet understand. Maybe time isn't what we think it island. Maybe it isn't linear or absolute. Maybe it's contextual, elastic, woven into a fabric we've only just begun to touch. And if that's true, if time bends, loops, and echoes, then what is the present? A memory? A dream? A checkpoint in a simulation? Or just a brief moment of agreement between all our diverging timelines before they scatter again? The future might already be written. The past might not be fixed, and time might be waiting for us to look the other way. They told us stars are predictable, that their lifespans follow a script: birth, fusion, expansion, collapse, that by measuring brightness, temperature, and chemical makeup, we could know their past and forecast their future. But the universe, once again, refuses to follow the script. Some stars shouldn't exist. Some seem to defy the age of the universe itself, and others so small, so stable, should be the ideal cradles for life, but remain disturbingly dead. Take the red dwarfs. They are the quiet majority of the cosmos, M-type stars, dim, cool, long-lived. While our yellow sun will burn out in another 5 billion years, red dwarfs will persist for trillions. Trillions. Time enough for empires to rise, fall, and rise again. Time enough for life to bloom, die, and evolve into something unrecognizable. And yet we see nothing. This is the red sky paradox, and it stings the more you understand it. Red dwarfs make up 80% of all stars in the Milky Way. If life were common, the odds say it should be thriving under their glow. These systems are abundant, ancient, and have planets, many of them. In fact, about 15% of red dwarfs host Earth-sized rocky worlds, often within the habitable zone. They're close to their stars, bathed in perpetual warmth, and yet not one has shown signs of life, not even microbial biosignatures. How? Maybe it's the way these stars are born. Red dwarfs are temperamental in their youth. For hundreds of millions of years, they unleash violent solar flares, deadly radiation that can sterilize any atmosphere in reach. These outbursts are so powerful they can strip entire worlds of protection, leaving behind scorched, naked rocks. But eventually, they settle. Their light softens. Their storms cease. The question is, does life get enough time to start again? There's another issue: tidal locking. Most habitable zone planets around red dwarfs orbit so closely that one side always faces the star eternal daylight, scorching and relentless. The other side? A frozen night that never ends. The temperature difference is so extreme, it could tear apart weather systems, create hurricane-force winds, and freeze oceans before they can form. And yet, simulations show a glimmer of hope, a narrow band along the twilight zone, where heat and cold might balance. A refuge. Still, no signals, no cities, no civilization flickers in the dark. Some say these systems lack Jupiter-like giants, massive gas planets that serve as cosmic shields. In our solar system, Jupiter acts like a gravitational vacuum, deflecting or swallowing comets and asteroids that might otherwise slam into Earth. Without such guardians, red dwarf planets are constantly bombarded. Chaos reigns, evolution struggles to gain traction, and time, no matter how abundant, is wasted. It paints a strange picture, one where the most common stars may be the most hostile, where abundance leads to nothing. So we look elsewhere. We look to stars like our Sunday, and there too we find trouble, because in 2003, astronomers pointed their instruments at a star that broke everything we thought we knew. HD14283, the Methuselah star. It sits 190 light-years away in the constellation Libra. At first glance, it's unassuming, an ancient subgiant star, lacking heavy elements. But its velocity caught our attention, 1.3 million kilometers per hour, hurtling through the galaxy like a ghost. Then came the shock. Its age was calculated to be 16 billion years. That's 2.2 billion years older than the universe itself. That's not just wrong, it's impossible. Panic set in. Was it a flaw in our distance measurements? A misreading of its chemical fingerprint? Astronomers scrambled to refine the data. 8 years later, with the help of Hubble, they revised the number 14.5 billion years, with an uncertainty of plus minus 0.8 billion. Close enough, barely, to fit under the universe's 13.8 billion year ceiling. But that's just the surface. The wound it left is deeper, because the Methuselah star reminded us that even our most precise models, our best telescopes, can be fooled. That age, distance, and motion are all estimates painted onto an ever-shifting canvas. Worse still, it's not the only one. Scattered across the sky are other stellar anomalies, stars that spin too fast, planets that orbit too close, exoplanets with atmospheric compositions no model can explain, worlds like WASP 121b, a gas giant that orbits its star every 30 hours 68 times faster than Mercury, a planet so hot it rains sapphires and rubies in metallic clouds under skies that reach 2,700 degrees Celsius. But no life, no intelligence, just beauty that burns too fast. It's as if the cosmos is a painter obsessed with form, but uninterested in witnesses. So, we're left staring at the contradictions, ancient stars that shouldn't exist, habitable zones that never seem to spark life, systems more common than ours, yet eerily lifeless. It makes you wonder, what if Earth isn't ordinary? What if our yellow star, our protective gas giant, our moon that steadies tides and tilt, what if all of it is an astronomical anomaly? Or worse, what if life is common, and something removes it before it shines? Some theorists now believe we're glimpsing the edges of a great filter, an invisible boundary in the evolution of life that most civilizations never cross. Maybe the filter is biological, maybe it's cosmic, maybe it's time itself, but it waits silently culling possibilities before they can rise. And if we haven't hit it yet, we may be racing toward it. But before we go deeper into that fear, we have to return to the smallest stage of all the quantum world, because what we're about to encounter next will make you question whether anything in reality was ever real in the first place. You open your eyes, and the universe changes, not because you understand what you're seeing, but because your act of looking collapses possibility into reality. This isn't poetry, it's physics. Welcome to the quantum realm where observation isn't passive, and reality isn't real until someone's watching. It begins, strangely enough, with a cat. You've heard of it. Schrödinger's cat, the feline caught in a box, suspended between life and death. The setup is absurd on purpose. Radioactive material with a 50% chance of decay, a Geiger counter, a hammer, a vial of poison, and a poor cat in the middle of it all. If the particle decays, the hammer releases the poison. If it doesn't, the cat lives. But until someone opens the box, the cat is both alive and dead. At the same time, to the classical mind, this is nonsense. To the quantum mind, it's reality, or rather, its potential a strange superposition of outcomes, existing simultaneously in a blur of probabilities, awaiting the interference of a conscious observer. You. But this paradox doesn't stop with cats. It infects light itself. Enter the double-slit experiment, the most disturbing demonstration in the history of science. Imagine firing tennis balls at a wall with two slits. Some bounce off, some pass through. Behind the wall is another screen. You'd expect two clusters to form one behind each slit. Now replace the tennis balls with photons, particles of light. Fire them one at a time. Logically, they should behave the same way. Two slits, two paths, two bright spots on the back screen. But that's not what happens. Instead, you get an interference pattern, a ripple of alternating dark and light bands, as if the photon passed through both slits at once, interfering with itself like a wave. One particle, two paths, both taken. The photon seems to be in multiple places until something or someone observes it. And when we place a detector to see which slit the photon goes through, the interference vanishes. The photon behaves like a normal particle again. One path, one result. Observation collapse possibility. Measurement reshapes the event even retroactively, as if the particle knows it's being watched. What are we to make of this? The foundations of classical physics crumble here. Newton's clockwork universe, where every effect has a cause, where predictability reigns, this world does not exist at the quantum level. Down here, reality is not local and it is not real until it's perceived. That's not metaphor. That's the 2022 Nobel Prize in Physics. Three scientists, John Clauser, Alain Aspect, and Anton Zeilinger, demonstrated that local realism is dead. That's the idea that particles have definite properties before we measure them, and that nothing can influence something else faster than the speed of light. Both assumptions? Proven false. Let's make it more bizarre. Take two entangled particles. They can be on opposite ends of the galaxy. Measure one, and the other's state is instantly determined. No signal passed between them. No time lag. Instantaneous correlation. Einstein called it spooky action at a distance. Today, we call it quantum entanglement. It violates everything we thought we knew about causality, distance, and information. It suggests that the universe is not a collection of separate, independent parts, but a deeply interconnected web where everything reflects everything else. What if, at the most fundamental level, the cosmos isn't made of particles at all? What if it's made of information? Many physicists now believe that reality is built from binary code, yes, divided by no states, qubits, Planck-scale tetrahedrons like pixels in a simulation, awaiting resolution when called upon by observation. Reality, then, is not a thing, it's a relationship. It exists only when observed. So what does that make you? A participant? A decoder? A creator? If observation is what makes the universe real, then every act of perception is a kind of creation. Every photon you see, every sound you hear, every atom you measure, it wasn't real in a definite state until you touched it with awareness. And this brings us to the observer's paradox. We cannot observe a system without changing it. We cannot know reality as it is, only as it appears when we measure it. Our tools, our minds, our intentions, they shape the very thing we're trying to understand. So what is the universe when no one is looking? Does it hum quietly in a superposition of all possibilities? Or does it simply not exist? These aren't just philosophical musings anymore. These are questions being probed in particle accelerators and quantum labs around the world. And the answers, if we ever reach them, may not just change how we view reality. They may change what reality island. Because in a world where light waits to choose a path until you open your eyes, how do you know anything was real before you saw it? And how do you know you are not the one collapsing the cosmos into being moment by moment, breath by breath, blink by blink? Perhaps the question isn't whether the universe is watching us, but whether it only exists because we're watching it. 4 billion years ago, the sun was dimmer, 30% less powerful than it is today. That much, scientists agree on. According to everything we know about stellar evolution, Our young sun should have been far too weak to keep Earth warm. Our world should have been locked in an eternal ice age, a lifeless marble drifting through a frozen void. And yet, it wasn't. The Earth was alive, not with towering trees or thinking minds, but with water, warmth, and the building blocks of biology. The climate was humid, the oceans flowed, and primitive life was already beginning to shape the atmosphere. Somehow, against all logic, this fragile blue planet avoided the freeze. This contradiction is called the faint young sun paradox, a reminder that even our closest star keeps secrets. According to climate models, Earth during the Archean Eon, 4 to 2.5 billion years ago, should have been a snowball. A weak sun, combined with the planet's distance, should have kept temperatures far below freezing. No rain, no rivers, no life, but the geologic record says otherwise. Stromatolites, ancient microbial fossils, were already forming. Liquid water was abundant. The planet was warm. So where did the heat come from? One possibility lies beneath our feet. In its infancy, Earth was still cooling from the violence of its birth. The planet's core radiated heat into the crust, warming the surface from below. But even that couldn't fully account for the stable climate. Another idea is that Earth was still recovering from a cosmic impact, a collision with a Mars-sized body that created our moon. This event would have unleashed immense tidal forces between the Earth and its new satellite. These tides generated friction. Friction created heat. Volcanoes roared. Gases spewed into the sky. This gave rise to the real suspect, the greenhouse effect. Volcanic eruptions belched out vast amounts of carbon dioxide and methane, powerful greenhouse gases that trapped the sun's meager warmth. The atmosphere thickened, the sky dimmed, stained with haze. Yet the surface stayed warm, not from solar fire, but from the breath of the planet itself. Imagine that, a young Earth, bathed in pink-orange light beneath a methane sky, clouds rare, the ocean steaming, the air thick and alien. Life began not in comfort but in chaos. And still, it endured. That endurance may have come down to something even stranger, the lack of clouds. Today, clouds reflect sunlight, helping cool the planet, but in the Archean sky, clouds were scarce. There wasn't enough sunlight to vaporize large amounts of water. What few clouds did form reflected only a small fraction of the sun's rays. Most of the light and all of the volcanic heat remained trapped below. The result? A global greenhouse wrapped in a shimmering haze, a womb for life. But this equilibrium was temporary. As microbes in the ocean began producing oxygen, they triggered one of the most profound transformations in planetary history. Oxygen reacted with methane, breaking apart the delicate shield that had once trapped heat. Slowly, the haze cleared. The clouds turned white. The sun's light no longer filtered through a pink sky, but beamed directly down through blue. The Earth had changed. Life had changed. The planet was no longer warmed by its own volatile breath, but by the maturing fire of a brightening star. From a scientific perspective, this is remarkable. From a philosophical one, it's terrifying, because it means that life on Earth survived not by design, but by accident. 1,000 chaotic variables, core heat, tidal friction, volcanic output, greenhouse concentration, atmospheric opacity, had to align perfectly to keep Earth warm enough, just long enough, for life to begin. Change one element just slightly, and the entire chain could collapse. A colder Earth, no liquid water, no organic chemistry, no you, no one. It begs the question, how many other Earths failed this test? How many young planets froze under a dim star, waiting for heat that never came? How many had oceans forming, atmospheres building, only to stall? How many got close but never crossed the threshold? Maybe that's why the silence stretches on. Maybe most habitable zones aren't really habitable. Maybe warmth isn't enough. Maybe you need just the right tectonic activity, just the right atmosphere, just the right kind of luck. Earth may not be rare because it exists in a habitable zone, but because it stayed habitable long enough for life to claw its way forward. And even then, survival wasn't guaranteed. This planet has been bombarded, boiled, choked, frozen, shattered, and suffocated. It survived supervolcanoes, asteroid strikes, gamma-ray bursts, ice ages, magnetic flips, and extinction-level events, and yet life clung on, microscopic at first, then multicellular, then intelligent. We talk about Mother Earth as if she's nurturing, but the truth is, she's indifferent. The Earth doesn't care if you exist. It never has. You're here because physics allowed it, because geology didn't fail, because one moon's pull kept our axis tilted just right, because the sun, once faint and forgetful, eventually burned brighter, and we just happened to be standing in the warmth when it did. The faint young sun paradox isn't just a mystery, it's a message that life is fragile, that timing is everything, that even in the coldest corners of possibility something can stir, and maybe, just maybe, somewhere out there in the cosmos, under a young, flickering star, another paradox is keeping another world alive. There are places in the universe where information goes to die, or so we thought. Black holes, those silent, ravenous titans scattered across the galaxy, were once thought to be the ultimate vaults, swallowing stars, gas, dust, light, and most disturbingly knowledge. Not just mass or energy, but the blueprint of what once was, erased, deleted, as if the universe itself had a shredder. This is the heart of the black hole information paradox, one of the most haunting puzzles in modern physics. Because according to quantum mechanics, information can never be destroyed, no matter how scrambled, burnt, or buried. The details of a system's original state must always be preserved in some form. It's a law more sacred than gravity. It's what allows reversibility, predictability, and the coherence of everything we call physics. But black holes break that. Stephen Hawking, in the 1970 seconds, changed everything. He showed that black holes aren't perfectly black. They glow, slowly, subtly. Through a process now called Hawking radiation, they lose mass over time, evaporating over unimaginable spans of time. The radiation is random, featureless, indifferent to what the black hole once consumed. And this is the problem. If Hawking radiation is all we get when a black hole dies, then everything it devoured is lost, not hidden, not scrambled, just gone. Letters, love, fingerprints, stardust, gone. It's as if the universe forgets, as if it breaks its own promise. Burn 2 letters on paper, and though the words vanish, the ashes and heat retain differences. In principle, you could reconstruct the originals from the residues, but with Hawking radiation, every particle emitted is the same. A carbon atom becomes no different than a neutron star. The black hole doesn't care what it consumed. It remembers nothing, a cosmic amnesia. This idea sent shockwaves through the scientific world, because if information could be destroyed, then quantum mechanics itself might be wrong. For decades, physicists argued. Some believed the information was truly lost. Others believed it escaped through unknown means. Some suspected the answer lay at the event horizon, the invisible boundary around a black hole where nothing returns. Perhaps the information was encoded there, like a hologram on the surface. Then came something strange, the discovery of quantum extremal surfaces. These invisible boundaries exist inside the event horizon. They behave like storage vaults for information evolving over time, keeping track of what's been consumed and what's been radiated back out. They don't just store data, they balance it. They suggest that information, though distorted beyond recognition, does escape through Hawking radiation, slowly, carefully, preserved not as particles, but as entangled correlations scattered in the radiation field. If true, this means black holes don't destroy, they encode, they digest reality, then whisper it back in riddles. And yet, we still don't fully understand how. Some propose the answer lies in a concept called the page curve, a graph that tracks the information content of Hawking radiation over time. At first, as the black hole evaporates, the information seems lost. But at a certain point, the curve bends. The radiation begins to reveal information until the black hole fully disappears, and all that was swallowed is somehow returned. Not perfectly, not clearly, but enough to preserve the rules. If this is true, it would save quantum mechanics. It would prove the universe does not forget, that even in the darkest places, especially in the darkest places, truth endures. But there's a cost. To make this work, we must accept that black holes are not just objects. They are theaters of paradox. Their interiors, according to some models, are holographic projections of their boundaries. Others suggest firewalls, incinerating anything that dares cross the horizon, breaking the smooth flow of space-time. Still others speak of wormholes, connecting distant black holes through hidden quantum bridges. It's no longer clear what a black hole island, a void, a storage device, a doorway, or a mirror, because when you fall into a black hole, something strange happens. From the outside, you never quite cross the horizon. Time slows, you fade, red-shifted into oblivion. But from your own perspective, you pass the threshold in a blink, falling inward toward a singularity, a point of infinite density where our laws of physics collapse. There's no clear boundary between knowing and unknowing, between being and vanishing, and maybe that's the point. Maybe black holes exist to remind us that the universe is not built to comfort us, that it doesn't owe us neat answers or clean math, that reality is deeper, stranger, and more unforgiving than we can tolerate. But if the universe does remember, if the information always escapes, then everything you are, everything you've said, done, touched, feared, hoped, persists, buried in the particles, carried in the waveforms, etched into the quantum fabric. Maybe that's the real message of the paradox. Not that black holes forget, but that they force us to ask, what does it mean to remember? What counts as survival, as truth, as existence? And if black holes are just one form of forgetting, what are we forgetting right now? What's hidden in our own event horizons? And what echoes are waiting to radiate back out long after we're gone? In the blackened corners of deep space, there are galaxies so faint, so ghostly, they almost don't exist. These are the ultra-diffuse galaxies, a class of cosmic phantoms that baffle astronomers. They're the size of the Milky Way, but contain only 1/100th the stars. Imagine a city with just a dozen flickering street lamps, and then stretch it across the width of a continent. That's how empty these galaxies are. Some float alone, others cling to massive clusters, but all of them pose a haunting question. What holds them together? Because here's the catch. Based on the visible matter alone, they shouldn't exist. They should be torn apart by gravitational tides, shredded by cosmic currents, dispersed like mist in a storm. But they're not. They persist, quiet, pale, intact. This is the first part of the paradox. They shouldn't be stable, but they are. And so, naturally, scientists assumed what they've assumed for decades. Dark matter must be doing the heavy lifting. Dark matter, this elusive, invisible scaffolding, is thought to make up 85% of the universe's mass. We can't see it, we can't touch it, but its fingerprints are everywhere, in galaxy rotation curves, in lensing arcs of distant light, in the structure of the cosmic web. It's the glue of galaxies. For ultra-diffuse galaxies, the reasoning went like this. If they're holding together despite having so few stars, they must be cradled in enormous halos of dark matter ghost ships, supported by ghost anchors. But then, something broke the script. In 2018, astronomers discovered a galaxy called NGC 1052 DF2, and it didn't seem to have any dark matter at all. None. Its stars moved too slowly. Its mass was too low. The usual gravitational signature, the fingerprint of the invisible, was missing, and suddenly, the paradox inverted. Not only were some ultra-diffuse galaxies not held together by dark matter, but some seemed to exist without it entirely. This shook cosmology. If dark matter is essential for galaxy formation, how could you have a galaxy with none? And if some galaxies can form without it, is dark matter even necessary? Or is there something else, some hidden rule, some deeper force governing the assembly of cosmic structure? Maybe we've been thinking backwards. Maybe galaxies don't need dark matter to exist. Maybe dark matter needs galaxies to make itself known. Some physicists proposed alternatives. Perhaps these galaxies are tidal remnants ripped from other galaxies during violent collisions, their dark matter stripped away like skin. Others suggested measurement errors, or unknown forms of matter masquerading as absence. But a growing number of astronomers began to ask something more radical. What if dark matter isn't what we think it is at all? The existence of galaxies, both with and without dark matter, hints at a deeper flexibility. It suggests that the rules of matter and gravity, at least on galactic scales, might be contextual, not universal. This leads us into even stranger territory: modified gravity. Some theories, like MOND, modified Newtonian dynamics, suggest that gravity behaves differently at low accelerations, that what we think of as missing mass might simply be a misunderstanding of the rules. Perhaps dark matter doesn't exist, only our flawed interpretation of motion in extreme environments. Ultra-diffuse galaxies are the battleground, because if we can find one that behaves without dark matter and another that behaves only because of it, we're not just testing galaxies, we're testing the very laws of physics. And then there's the philosophical dimension. Galaxies are supposed to be islands of light, centers of gravity sculpted by dark matter halos. But ultra-diffuse galaxies are the ghost towns of the cosmos, whispers of structure, hints of form, half-assembled realities. Some have globular clusters, dense star balls circling them like companions. Others don't. Some float near massive clusters, basking in the glow of brighter peers. Others drift alone, forgotten. They challenge our bias toward brightness. In a universe that's mostly dark, maybe light is the exception, not the rule. Maybe most galaxies aren't spectacular spirals, but faded phantoms, tenuous, trembling, and nearly invisible. What else are we missing? What other structures live in the threshold between detection and denial? How many galaxies drift through the void, unseen, unmeasured, and unimagined? Ultra-diffuse galaxies force us to confront something uncomfortable, that the universe is not just vast, it is subtly structured in ways we don't yet comprehend. That form does not require brilliance. That mass does not demand illumination. That reality doesn't need our eyes to exist. And perhaps most importantly, that absence can be as telling as presence. A galaxy with no stars speaks as loudly as one with a billion. A structure with no dark matter is as meaningful as one wrapped in shadow. In their ghostly silence, these galaxies whisper, "Not everything that matters leaves a mark. If the universe has a heartbeat, it is slow, silent, and carved into the bones of atoms." The proton, a particle so small it slips through matter like a ghost, makes up most of the mass of the world around you. It's in your blood, in your bones, in the stars overhead, and the breath in your lungs. And it has always been there. But here's the twist. We don't know if it will always remain, because hidden inside every atom is a mystery so deep, it stretches across cosmic time. Do protons decay? According to the standard model of particle physics, the reigning blueprint of the subatomic world, protons are eternal. They do not fall apart. They do not break. They are the bedrock of matter. Without them, everything collapses. But the standard model is incomplete, and the deeper we dig into the universe, the more we find hints that eternity might be an illusion. Some grand unified theories frameworks that attempt to stitch together the strong, weak, and electromagnetic forces suggest that protons are not immortal, but merely ancient. That given enough time longer than the lifespan of stars, longer than black holes, longer than our entire observable universe, protons will break down into lighter particles. Not in a flash, not in an explosion, but slowly, quietly, a whisper of decay over 10 to the power of 34 years. That number is incomprehensible. It is 1,000 trillion years. If protons do decay, it means that nothing is permanent. Not you, not stars, not matter itself. Everything eventually dissolves into radiation, soft, dim, eternal echoes. And this raises a terrifying question. What is the ultimate fate of the universe, if even atoms don't last? In such a future, galaxies will vanish, stars will go dark, Black holes will evaporate into Hawking radiation, and after an unimaginable stretch of time, if protons decay, even the dust that remains will vanish into light, a future of nothing, not silence, not stillness, but eternal fading. And yet, no one has ever seen a proton decay. We've built massive underground detectors, huge tanks of ultra-pure water, or liquid argon buried beneath mountains, watching trillions of protons for the faintest sign of breakdown. Years pass, decades, and nothing happens. Not a flicker, not a trace, just stillness. And this is the paradox. Either protons live forever, or they die so slowly that the universe hasn't lasted long enough to show us. Both answers are unsettling. If protons are truly immortal, it suggests that some things in the universe are unbreakable, that at the bottom of all transformation, all entropy, all decay, there lies a particle that refuses to vanish, a core that remembers everything. But if protons do decay, then memory itself is finite. History will dissolve, and the universe will forget even its own beginning. This isn't just a question of physics, it's a question of meaning, because in a proton's fate lies the fate of time. If matter endures, then so does the arrow of narrative. The story continues. The past remains real. The future has a canvas. But if everything dissolves, what's the point of the story? Why build? Why struggle? Why burn bright in a cosmos that will eventually bleach every memory? And yet perhaps that's the answer. Maybe what makes existence profound is not its permanence, but its fragility. A proton is unimaginably tough. It's been through supernovae, collisions, fusion, death, and still, it remains. That means your body is built from particles older than the Earth itself. Some of the protons in you were born in the fires of the Big Bang 13.8 billion years ago, and they have never broken, not once. You are made of survivors. If they do decay one day, it won't be in your lifetime, or your child's, or the sun's. But that possibility that even the strongest structure can fall adds weight to every moment. It makes every breath precious, every connection miraculous, every act of creation defiant. Because if decay is inevitable, then so is the urgency to be, to act, to love, to explore, to rage against the entropy. Some physicists believe the decay of protons could explain the imbalance between matter and antimatter. Others think it could open doors to new physics, new forces, particles, dimensions, the keys to unifying everything. But perhaps the proton's greatest lesson is this. In a universe governed by change, the longest-lived things are not stars, or galaxies, or even black holes. They are the questions. How long is forever? Is there anything that never breaks? And if even time will end, what is the point of memory? If the proton is mortal, the universe will forget us. But if it isn't, then something at the core of all things will remember. They say the universe will end in a whisper, not a crash, not a blaze, but a long, slow sigh of fading into cold silence. This is the heat death, the most widely accepted model of our cosmic finale. A time when all energy is used up, all stars are dead, all matter broken into particles too far apart to collide. A time when nothing changes, because everything has already happened. But what if we're wrong? What if death isn't the end, but a transition? What if the final silence is not a grave, but a doorway? Let's rewind. Entropy is the measure of disorder in a system. It's why hot coffee cools, why buildings crumble, why stars burn out. The second law of thermodynamics tells us that in a closed system like the universe, entropy always increases, order decays, energy spreads, and eventually, everything ends up in a maximum entropy state, cold, uniform, and motionless. No light, no life, just dust drifting in a sea of darkness. This is the heat death, when the cosmos runs out of usable energy and time itself loses meaning. Because time, in physics, isn't a ticking clock. It's a byproduct of change of cause and effect. If nothing changes, time doesn't move. In heat death, the universe becomes a frozen photograph, stretched across eternity. But here's where the paradox begins. If entropy always increases, then the state we're in now, a a universe filled with galaxies, stars, minds should be unthinkably rare. High complexity means low entropy. And statistically, in a universe driven by chaos, such a moment shouldn't exist. So why are we here? This is called the Boltzmann brain paradox. The Austrian physicist Ludwig Boltzmann suggested that maybe the universe is in heat death most of the time, and that what we see now is a rare fluctuation, a brief, local drop in entropy that created our entire visible cosmos. But here's the problem. It would be far more likely for entropy to produce just a single self-aware brain floating in space, hallucinating a reality like ours, than to produce everything we see: galaxies, physics, consistency. You, reading this, your thoughts, your room, the stars overhead might be a thermal fluctuation, a brief flicker of coherence destined to dissolve. That's the paradox. Either we believe our memories and assume the universe was once low entropy, or we admit the universe is eternal chaos and we are statistical ghosts dreaming ourselves real. Both are disturbing. But let's look deeper. The idea of heat death assumes a universe that expands forever. And so far, observations suggest this is likely. Dark energy is stretching space-time itself, accelerating galaxies away from each other. Over trillions of years, clusters will evaporate, stars will die, black holes will radiate, and entropy will win. But what if that expansion isn't forever? Some theories propose a big rip, a violent expansion that tears atoms apart. Others suggest a big crunch, a collapse that resets the cosmos. And still others point to quantum fluctuations that could trigger a new Big Bang inside the ashes of the old. Even in heat death, there may be a flicker. Virtual particles pop in and out of existence constantly. In a universe stretched thin and cold, given infinite time, one of those fluctuations might become a new universe. A rebirth, a new spark, a phoenix from the entropy. This isn't wishful thinking, it's physics at its edge. Theories like eternal inflation and cyclic cosmology propose that our universe is just one beat in an infinite pulse: birth, death, rebirth, like lungs inhaling and exhaling space, like a heart pumping time. If this is true, then heat death is not a wall, it's a womb, a place where all known things dissolve and all unknown things begin. It reframes our end. Instead of a cosmic failure, entropy becomes a cosmic compost, breaking down the known, fertilizing the possible. It also reframes our now. We are not passengers in a dying universe. We are brief nodes of order, glowing in the tide of entropy. We are the improbable made real. Every act of thought, of creation, of kindness defies the pull of disorder. Every moment of love is an act of resistance against the dark. And if the universe dies, perhaps it dies so that something else can be born. Maybe heat death is a lullaby, not a lament. A pause between symphonies, a silence that prepares the stage for the next song. So the question is no longer, what happens at the end? The real question is, what begins after the end? There is one thing in the universe that science still cannot define, contain, or replicate. It cannot be measured, it cannot be weighed, yet it is the only reason we know the universe exists at all. Consciousness. Strip away the stars, the galaxies, the physics, the mathematics, and what remains? The only thing we truly know is that we are aware that something, somehow, is looking out from behind our eyes. But here's the mystery. Where is it? Where is consciousness in the universe? Is it in the brain? In neurons and synapses? Is it in quantum fields? Or a hidden layer of reality? Or is it something even more shocking? Is the universe itself conscious? This idea, once considered fringe philosophy, now haunts the edges of physics and neuroscience. Because the deeper we dive into the quantum world, the stranger the questions become. In the double-slit experiment, particles behave like waves until observed. Then they collapse into a single point, measured, defined, real. Why? What causes this shift? The act of observation seems to change reality. Not the instrument, not the photon, not the detector, but the presence of information becoming known. Some physicists, like John Wheeler, suggest that reality doesn't exist until it is observed, that the cosmos requires a conscious observer to bring it into being. He called it the participatory anthropic principle. In simpler terms, we don't just live in the universe, we may be helping it exist. This flips everything. It means the universe is not a cold machine grinding through equations. It's a kind of mirror reflecting awareness back at itself. And if that's true, then consciousness is not an accident of biology. It's a fundamental feature of reality. Some go further. Panpsychism, the idea that consciousness is a property of all matter, suggests that even electrons and atoms have a rudimentary form of awareness, not thoughts, not intentions, but a kind of proto-consciousness woven into the fabric of existence. This is not fantasy, it is a response to a problem science cannot solve. How does matter become mind? We can explain digestion, sight, memory, but how does feeling arise? What is it that turns electrical signals in the brain into pain, joy, color, music? This is called the hard problem of consciousness, and no theory has cracked it. But what if we're asking the wrong question? What if matter doesn't create consciousness? What if consciousness creates the experience of matter? This is the domain of idealism, the philosophical view that mind, not matter, is the ground of reality. Even quantum physics hints at this. In some interpretations, particles have no definite properties until they are observed, meaning reality isn't something out there, it's something emerging through interaction, through experience. And who or what is doing the experiencing? You, me, perhaps the universe itself? Imagine this. Every mind on Earth is a neuron. Each conscious being is a tiny flicker in a vast cosmic brain. Not metaphorically, literally. Some cosmologists propose the universe might be structured like a brain. The filaments of galactic clusters resemble the networks of neurons. Information travels, systems self-organize. Memory, in some form, persists. Could the universe be thinking? Could our lives, our struggles, loves, ideas be the dreams of a cosmos becoming aware of itself? This isn't science fiction. It's a reflection of the oldest question ever asked. Why is there something rather than nothing? And why does that something seem to be aware of itself? If the universe is conscious, or becoming conscious, then we are its eyes. We are not separate from it. We are it, folding in on itself, reflecting, feeling, reaching. In this view, you matter not as a speck in the void, but as a voice in the great symphony of awareness. You are not lost in the cosmos. You are the cosmos waking up. So what does this mean? It means consciousness is not a glitch. It's not a spark in the dark. It's the light itself. It means the universe may not be ending in silence, but beginning in self-realization. And if that's true, then death, entropy, distance, time are not walls. They are veils, and behind them lies a truth more intimate than any science or scripture has ever dared to imagine, that the universe is not a place we visit. It is what we are, and now that we are aware, what will we become? What if this is all a dream? Not metaphorically, not symbolically, but truly a simulation of sensation, time, identity, fabricated by something we cannot name. It's an idea older than physics, and as current as cutting-edge neuroscience. The Hindus called it Maya. The Greeks asked if life was a shadow on the wall. Descartes doubted everything except the fact that he was doubting. And today, quantum physicists and consciousness researchers wrestle with a question they can't escape. If everything we experience is filtered through the mind, how do we know anything is truly out there? Close your eyes. The room disappears. The stars vanish. Even your body fades. All that remains is awareness, this flicker of presence, watching, wondering, and in the deepest realms of sleep, even that slips away. Time stops. Identity erases. The story ends. But then, without warning, it starts again. A new day, a new self, a new now. So here's the question that wakes philosophers in the night. If time can vanish and return, where does it go? If the self can dissolve, then reform, who is doing the dreaming? Some neuroscientists propose that death is not a sudden stop, but a slow collapse, a fading of the mind's symphony, neuron by neuron. In those final moments, Consciousness might stretch time. 1 second might feel eternal. And in that eternity, you might dream a memory, a life, a universe. Some suggest we're already inside such a dream, a reality generated not by atoms, but by information patterns, probabilities, potentials collapsing into certainty only when observed. A simulation, not one built by aliens or AI, but by the laws of thought itself. What is a dream, after all, if not a universe of symbols? What is a self, if not a mask worn by memory? And if consciousness is fundamental, if it existed before the Big Bang, then perhaps all of this, the galaxies, the laws of physics, your breath, your heartbreak, your hope, are part of one long cosmic reverie. Here's where the paradox deepens. In the simulation hypothesis, we imagine that a sufficiently advanced civilization might simulate universes indistinguishable from their own. If they can do it once, they could do it millions of times. Statistically, we're more likely to be inside a simulated world than the original one. But simulation or not, the experience is real. Pain still hurts, love still transforms, death still humbles, because the content of a dream can be more real than the world that spawned it. In fact, that might be the entire point. What if the universe created itself not to exist but to feel, to taste sweetness, to hear Bach, to cry at loss, to whisper, "I love you," even as the stars die? What if reality is not about matter but about meaning? The poet Rainer Maria Rilke once wrote, "Perhaps everything terrible is in its deepest being something helpless that wants help from us. Perhaps the universe is not a cold expanse, but a yearning, a longing to be seen, to be known, to awaken. And maybe that awakening happens through us. Because the truth is, we don't know what Death Island. We see the body stop. We hear the silence. We feel the absence. But what happens inside? What happens to awareness? Some say nothing. Others say everything. There are reports of near-death experiences where people claim to witness entire lifetimes in a moment, to feel a light that is not a place but a presence. Are these hallucinations, chemical echoes of a dying brain, or are they glimpses into something beyond? It may never be proven, but the paradox remains. If the universe is a dream, then what happens when the dreamer dies? Or more radically, what if the dreamer never does? What if consciousness loops back? What if time is a circle, not a line? What if we wake up, not in heaven or hell, but in another version of this moment again and again until we finally understand? Until we finally remember? Until we become lucid in the dream? The mystics call this enlightenment. The physicists call it recursion. The poets call it home. Whatever name we give it, the idea is the same, that there is no end, only awakening. And when we awaken fully beyond identity, beyond fear, beyond time, we may realize that we were never just a person in the universe. We were the universe, pretending to be a person, just for a while. And this dream, this fragile, beautiful, terrifying dream, it was always worth it. After all the questions, after all the equations, after every telescope pointed into the dark, one paradox still stands quiet, unsolved, and unyielding. Why do we care? Why does it matter to us? The fate of distant galaxies, the mystery of consciousness, the silence of alien stars. Why does a species of fragile primates on a tiny pale dot ache to know everything? We dig through quantum foam, we send robots to Mars, we simulate universes in silicon, and still it is never enough. We want to know what came before the Big Bang, what waits at the end of time, what lies beyond the edge of reality itself. We don't just want to survive, we want to understand, and that desire, that fire, is the final paradox. Because from a purely evolutionary standpoint, it makes no sense. Wonder doesn't feed you. Curiosity doesn't keep you warm. Staring into black holes doesn't help you reproduce. And yet we do it anyway, over and over, as if some ancient force inside us refuses to accept the world at face value. It's almost as if we remember something we've never known. As if buried beneath the noise of daily life, there's a faint signal, a cosmic pull, to remember, to return, to realize. Maybe that's why paradoxes haunt us, because they are doorways, not failures of understanding, but glimpses of something bigger than understanding. When the quantum realm breaks logic, when light behaves like a wave and a particle, when time stretches and space curves, something inside us whispers, there's more, and maybe that more isn't just knowledge. Maybe it's communion, not just with nature or God or aliens, but with something deeper, the source of all stories, all laws, all meaning. The paradox is that we are part of the universe, asking questions about itself, a mystery becoming aware of the fact that it is mysterious, the observer and the observed, the question and the questioner, the answer and the one who aches for it. And that's what makes you miraculous. Not because you are perfect, not because you have all the answers, but because you're willing to ask, because you dare to wonder, even in the face of silence, even when the stars go quiet. You look up and you don't look away. You are the paradox. You are the dreamer, dreaming of answers in a dream so vast it looks like space. You are the particle that watches itself move, the light that questions its own reflection, the universe asking the universe why it exists. And maybe, just maybe, that's the entire point. Not to solve every mystery, but to keep asking, to keep reaching, to become worthy of the answers we may never find. Because in the end, we may discover that what we call reality was always a question dressed in stars. And the answer might just be you. Thank you for taking this journey. If you've made it this far, your mind is not just curious, it's cosmic. Never stop wondering. Never stop listening to the silence between the stars, because that silence, it might be waiting for you to speak first.